Welcome to Chapter 16, Part 2. We're going to be continuing doing some problems in Chapter 16. We're going to start with problem 16.14, back to testing blood cholesterol. They say that the mean blood cholesterol level for all men ages 20 to 34 is 188 milligrams per deciliter. We suspect that the mean for cross-country runners is lower. So they want us to state the hypothesis and use the information in exercise 16.13. That is, that they did a sample of size 14 that had a mean of 172 with a population standard deviation of 41 to do a z-test. So we need to find out if the results are significant at three different alpha levels, alpha of 0.1, 0.05, and 0.01. But we first have to state our null and alternative. And the way we do that is looking into the problem, we have to figure out what we're trying to test. And it said here that we suspect that the mean for cross-country runners is lower. Is lower is key to us to tell us that we're doing a left-tailed test. So as you can see up here, my null hypothesis is that the mean blood level is 188 milligrams per deciliter. Now, our alphas that we're looking at are 0.1, 0.05, and 0.01. So our next task is to calculate the test statistic. Now again, remember our test statistic is how many standard deviation our sample mean is in the null hypothesis distribution. So we have to remember what the null hypothesis distribution is. So the null hypothesis distribution has a mean of 188 and the standard error of 41 divided by the square root of 14. So if I wanted to see how many standard deviations my sample mean is, I just find the z-naught, which is just going to be my x bar minus mu naught, the value of my null hypothesis distribution, divided by that standard error, sigma, over the square root of n. So I input those values. The sample mean, which we found in 1613, or were given to us, is 172. The null hypothesis mean value is 188, and the standard error is 41 divided by the square root of 14. When I do that equation, I get my test statistic as negative 1.46. Now, to calculate the p-value for a left-tailed test, it's just the probability that z is less than my test statistic. And from the chart, I get, so it's 0.721 is my p-value. Oh, it's 0.0721, excuse me. Let me correct that. So we're going to compare this p-value against the different significance level that they ask us to. So and I better correct those. So what we're going to do is we're going to put a sign in between these two, between the p-value and the specific alpha that we're looking at. So the p-value of 0.0721 is less than 0.10. The p-value that we got, 0.0721, it's greater than 0.05. And, of course, 0.0721 would be greater than 0.01. So in the first one, at the significance level of 0.1, we were willing to accept the probability of a type 1 error 10% of the time. Our sample told us, the sample mean that we got said we would make an error about 7% of the time. So in other words, our sample is telling us that we'll make that error less than what we were willing to accept. That's a good thing. So in other words, we'll make a mistake less than the number of times we were willing to make a mistake. So that would be a good thing. So again, the p-value being less than alpha is when we reject. So in this one, we would definitely reject. So if let's look at the next case. 0.0721 is greater than 0.05. So our p-value is greater than alpha. In other words, we're going to make a mistake more than what we were comfortable making. So we'll do it, if we did this thing 10 times, 7 times we would make a mistake, whereas we were willing to only accept 5. So, or I should say if we did it 100 times, 7 times we would make a mistake. 5 we were willing to accept. So too much probability of an error. So we will not reject for that one. And again, in the last case, our p-value being greater than alpha would tell us we do not reject the null hypothesis. So we see that we would reject at a 0.1 alpha significance level, but we do not reject the null hypothesis at a 0.05 or a 0.01. That sample mean is not significant. So for 1615, it asks how large a sample is needed to cut the margin of error in 16.13 in half. So we're talking about that 90% confidence interval to cut it in half. Well, if we want to cut that margin of error in half, that's like just saying take that margin of error and divide it by 2. So let's look at the formula. Z alpha over 2 times sigma over m. But in place of m, I want that m cut in 2. Well, remember, in the denominator, if you have a fraction, you invert and multiply. So it's just like saying 2 times our critical value, Z alpha over 2 times sigma over m, that quantity being squared. If I pull that 2 out of the parentheses, just a little bit of algebra going on, that means I have to do 2 squared and pull it out. I'd have 4 times, and in parentheses, Z alpha over 2 sigma divided by m squared. But that's just n. So, in other words, it would equal 4n. So if I cut my margin of error in half, I would have to multiply my original sample size by 4, and that was 14. So I'd have to have a sample size of 56. So my margin of error, again, for my original sample size is 14, so therefore I take 4 times 14, which is 56. So that's the sample size I would need if I wanted to cut my margin of error in half. And let's look what would happen if I wanted to cut it in a fifth. Well, again, I do the same technique. I'm going to, if it's m over 5, then remember it's like inverting and multiplying by 5 over m. So to pull that 5 out of that parentheses, I need to square it since that whole quantity is being squared. And so I'd have 25 times n, because Z alpha over 2 sigma over m squared is just n. So I'd have to take my original sample size, which is 14, and multiply it by 25 to get how big a sample size would cut it in a fifth. That's just an example to show you if it was something other than half, how it would work. Now, how large, the second half of this problem was how large the sample size is needed to cut the margin of error to plus or minus 5 milligrams per deciliter. Well, I used a straight formula. We're doing a 90% confidence interval because that's the interval that was in in question 16.13. So for that, the critical value is 1.645. The sigma was 41 divided by 5. That's the margin of error we want to have. We are being asked to have no more than. And we square that quantity. So we get 181.95. So we have to round that to the next integer. So we would need a sample size of 182 for a 95% confidence interval to have a margin of error of plus or minus 5. And that's how we'd work that problem. Now in problem 16.16, we're going to increase the sample of our cross-country runners from 14 to 56. And we're going to do our hypothesis test. In other words, we believe that the cholesterol level of these runners is less than the normal. So we're going to look at it at a 0.1, 0.05, and a 0.01 significance level. So we run through the same technique. We have our null hypothesis distribution has changed just a bit. The mean is still 188, but the standard error is 41 divided by the square root of 56. And when we do our calculation, finding how many standard deviations our sample mean is in the null hypothesis distribution, we get that that's negative 2.92. So when we calculate the p-value for this, we get 0.0018. Now, when we look at this one, all of these, at every significance level, we reject the null hypothesis distribution for this problem. And what we find for this particular problem is when we get a larger sample size, even small differences can be very significant when our sample size gets larger. So this concludes Chapter 16, and we'll be starting 17 soon. So I hope this helped and gave you some good examples, and we'll be going over some of the commands from Mini-Tab 4.